Okay, this video is going to be a bit of a follow-up to a couple different concepts. We're going to keep going through some more two-dimensional motion practice, and we're going to go back to something that we talked about a long time ago with regard to the difference between distance and displacement and speed and velocity. If you'll recall, displacement is a vector. And it represents your change in position and because it's a vector, that means direction matters. On the other hand, distance is the scalar version of displacement. It's a scalar, as I was saying. It's not your change in position, but it's your total path length traveled. So here we're ignoring direction while we just follow how far something has actually moved along its path. Velocity, it goes with displacement. That's the vector version of your change in position over time. Speed is the scalar version of the same thing. It ignores the direction but just looks at how far you've gone in that period of time. So with that in mind, we can get some practice doing our two-dimensional vector adding with displacement and then seeing how that's different for distance and then as a result being able to compare speed and velocity. So just to give us a couple vectors to work with, the plane flies 250 kilometers north, 20 degrees east. North, then east. I draw it a little bit less than 45 and my angle goes where I started, so that's 250 kilometers. And then east, north, 25 degrees, 300 kilometers. So that's my second displacement in 2 hours. Compare the speeds. I can plane the plane's average speed and velocity. I'm going to leave this in kilometers an hour, and then when I get to my final answer, I'll have kilometers per hour, which is an acceptable unit for speed. Labeling this triangle, this is my adjacent side, this is my opposite side. Hopefully we've been working with components enough then that you will see that this one is 250 sine 20. If you want to know how you get to that point, you can simply go back in previous videos. 250 sine 20 works out to be 85.5. Go to a thinner pen here. I'm finding this one a little thick. This one will be our 250 cos 20 then. And that's 235 kilometers. So this is my delta D1N, and this is my delta D1E. Now I can do the same thing for the 300 kilometers. Remember, your arrow always points to your opposite side, and opposite that ratio is the sine ratio. So 300 sine 25 is 127 kilometers. And here, adjacent to the angle or beside the angle, we have our 300 kilometers cos 25. which works out to 272 kilometers. Now I'm going to use a chart to keep these things straight as I try to find my total displacement. I have a north for delta D1 of 235 kilometers and an east of 85.5 kilometers. And those are both in my positive directions, north and east. For my delta D2, I have an east here of 272 kilometers and a north of 127. And that's my delta D2. For my total displacement, I can simply add my individual displacements. So for this one, 235 plus 127 gets it to 362 kilometers. And 85.5 plus 272 works out to 357.5 kilometers. Again, when recombining vectors, it's not necessary, but it's somewhat helpful to be standard. My north here is a little bit bigger than my east, so I will do it in that order. You can do it in whatever order you want, as long as you get your heading right at the end. So using the Pythagorean Theorem, we can come up with the displacement total. First of all, the magnitude is going to be, h squared equals, I'll just jump to the square root of 362 kilometers squared plus 357.5 kilometers squared so my Pythagorean resultant is 508.8 kilometers. In my heading here, I've gone north and then I've gone east. I always put my angle at my start, so this is my opposite side and this is my adjacent side when considering my tan. And so my theta is going to work out to be 44.6, pretty close to 45 degrees. 44.6 degrees. So that gets me my displacement. I'm actually trying to get speed and velocity. So remember, velocity is the one that's tied to displacement. Velocity is equal to the displacement divided by time. So here I have 508.8 kilometers divided by 2 hours. I need to carry my direction around because this is a vector, so I need to make sure I include that. And that's going to be 254.4 kilometers per hour, north 44.6 degrees east. So that's my velocity. And that's a big long problem, especially in comparison to what we're going to do if we want to just get the speed. The speeds can be much easier. For a speed, we consider the total of delta D1 and delta D2, but we ignore the directions. So for a speed, for a distance, delta dt, it's going to be delta D1 plus delta t d2, but you'll notice the lack of arrows in this equation. That basically means I can ignore the directions entirely and just do 250 kilometers plus 300 kilometers for a total of 550 kilometers. Now my speed, which is equal to my distance over time, is my 550 kilometers divided by my 2 hours, which works out to be 275 kilometers per hour. And there's no direction given here. If I compare these two numbers, the other one was 275 kilometers per hour. We can see that my speed is a little bit bigger than my velocity. They're actually pretty close in this example. Speed is always going to be equal to or bigger than velocity. Any change in direction will lower your displacement, but it doesn't lower your distance. And so it lowers your velocity, but it doesn't lower your speed. So you can see here that slight change in direction made the velocity a little bit lower than the speed. But because the two vectors that we added in the first place in this question were fairly similar, it's not a big reduction. I'm going to do one more speed and velocity question, but I think I'm just going to start a new video so that we can have them separate.